Okay, for this lesson we are moving into chemical energy. This is a calculation-based section with some theory. So you are going to need your data booklet and a calculator handy when you do this. Your data booklet should be open to page 5, so it should have this table where it says standard heats of formation of selected compounds at 25 degrees Celsius. So starting off this section, it talks about cell phones versus skidoos, and it asks which is powered by fossil fuels. So the last section, or the last video that you watched, or should have watched, talked about the different forms of fossil fuels. So again, there are 3 forms of fossil fuels. We have coal, oil, and natural gas. All 3 of these are heavily relied on here in Alberta specifically. Roughly 70% of our electricity that we rely on every day comes from the burning of fossil fuels. So anytime you plug something into the wall, 70% of the energy, unless you are not wired to the electrical grid, 70% of the energy that is coming out of that outlet is coming from the burning of coal, which is fossil fuels. So that being said, a cell phone versus a skidoo. A cell phone, if you think about it, most people plug their phones in at night. Okay? They don't put them on the windowsill to charge. Well, they might put them on the windowsill, but that cord is plugged into the wall. Okay? But what I was trying to get at is they don't put their cell phone in the window for the sunlight to charge the phone. Okay, so technically a cell phone will use fossil fuels because you're using the electricity that is coming from the wall. A skidoo is pretty self-explanatory because you're putting gasoline and engine oil into the object, so into the vehicle. And both of these are fossil fuel based. So both of these substances require fossil fuels. Now, when we have a combustion reaction, so you should remember combustion reactions from back the beginning of chemistry unit. So you have CXHY, so this is a hydrocarbon, which is a fossil fuel. You are burning it in the presence of oxygen, which is O2. And then your molecules are rearranging into carbon dioxide, CO2, and then water. So these bonds must be broken in order to release energy. Now we use that energy for power purposes to move forward or to light up our phone to make it work. Okay, so once that energy has been released, the bonds then reform at the end to create a new substance, which is why we have CO2 and H2O instead of our original reactants. So there are many energy forms that are released during the combustion process, but the 2 that we focus on, specifically number 2 here, are radiant energy, which is infrared and visible light photons, which you should remember from that EMR project that I asked you to do. And then thermal energy. So thermal energy is talking about heat. So this is the transfer of energy from molecules or atoms at a higher temperature to those at lower temperature. Thermal energy is always going to move from a higher temperature, so hot, to cold. Now, this can be related to the heat of combustion. So this is the amount of heat or thermal energy that is released when a substance undergoes a combustion reaction. So how much energy do we get from a certain substance is really what it's referring to. So exothermic change is talking about a release of energy. So it says explain the diagram. So in this diagram, we have reaction pathways. So this is as the reaction progresses. This is the potential energy in kilojoules. Okay, so we have our reactants, which are higher energy than our products. So what that means is as the reaction occurs, the reactants would have a higher energy than the products, which means that the difference had to go somewhere. okay, because you can't technically lose any energy, okay, it just has to be transferred to something else. So that's what I explained here. So energy of the reactant or reactants is higher than that of the products. This implies that the energy that was lost in this area was given off to the surroundings. Now, if you have a higher energy in a reactant and lower in the product, your heat of combustion is negative. So if you have a negative kilojoules, that will tell you that you're an exothermic reaction. Endothermic reaction, on the other hand, is the absorption, so the taking in of energy. So what would a graph look like if you had endothermic change? Well, obviously it can't look exactly like the previous, because then that would imply that it's exothermic. So let's just go back for a second. So we went from high to low. So what's the opposite of that? If you're talking about exact opposite, it would start from low and go to high. That is an endothermic change. Okay, so you're going to have, I'm just going to put R for reactants, goes to P for products. Okay, so as you can see here, this is an energy change that had to be taken in. So energy absorbed. So would delta H be positive or negative? So would the heat of combustion be positive or negative? Well, negative meant that it was given off, which means positive had to be taken in. So calorimeters are devices that can actually measure how much change is occurring. So if you're looking at a calorimeter, and now we would normally do a lab, but unfortunately we can't. What would happen to the temperature if it was an endothermic reaction? Think in your head. If you thought colder, so temp would drop, you are correct. So temperature decreases. Now what would happen if the temperature if it was an exothermic reaction? So temperature would do the opposite, increase. Now this is the calculation part, so bear with me, go slow. This calculation looks challenging, it's actually not that bad. So standard heats of formation is the energy, is the energy change for a chemical reaction that involves the formation of a compound from its elements determined at standard conditions. So standard conditions meaning normal temperature, normal pressure, etc. So the heat of formation of any element is 0. Sorry, I should have kept my highlighter. That is super, super important. So if you have an element, its heat of formation is 0. Right away, you just put 0 in. Now, the heat of formations of compounds vary, so that's what this table on page 5 in your data booklet is for. Okay, so ammonia's heat of formation is negative 55.9 kilojoules per mole. Benzene is positive 49.1 kilojoules per mole, and so forth. It also tells you in the table at the bottom, elements are given a value of 0. Okay, so you don't really have to memorize it. It's given to you right in your data booklet. It also tells you that if you have a negative sign, it tells you you're exothermic. And if you have a positive sign, it tells you that it's endothermic. So you have a lot of information in your data booklet. Just learn how to use it. Okay, so this is your formula in your data booklet. That's this one down at the bottom. Okay, now I know it looks scary. It's not actually that scary. So the symbol, this symbol, I don't even know what they call this symbol, but I call it the E. Okay, the fancy dancy E. What it really talks, or what that really means is the sum. Okay, and the sum means adding. Okay, so you're adding, N represents moles, so however many moles you have of a certain substance, and then you're taking the heat of formation of that specific substance, multiplying it by the moles, and then adding it to the other product that you have, because you're doing products minus reactants. Okay, again, this is probably Greek, but it'll make more sense when we do the calculations. Okay, so it says calculate the energy change for the combustion of methane. So here's our reaction. Now the key thing that you need to know is you have to balance first. You cannot do any of these reactions without balancing. So this is bringing back your chemistry. So combustion reactions, you balance C's, H's, then O's. And look back in your chem notes if you forget, or send me a message and I can kind of help you and guide you. Maybe I can find you a video to help balance. Okay, so balancing, this arrow is your fence. You must make sure that the right side of the fence and the left side of the fence equal each other. So we have one carbon atom on this side, we have one carbon atom on this side. So that's good. We have 4 H's here, but only 2 on this side. So what do you multiply by 2 to get it to 4? 2 times 2 is 4. Now, O's are always the last one. So, again, this is my fence. On this side has to equal this side. So I have 2 right there, and then I have 2 H2O. So that's applied to both of these. Excuse me. So technically I have 2 O's there. So I have a total of 4 O's on this side, but only 2 here. I need to make it 4. You multiply this by 2 as well. So now you have a balanced chemical equation. Now you can do the heat of combustion. Okay? So, now sometimes they have R, sometimes they have C for heat of combustion or heat of reaction, but it's the same thing. Okay, so we start with our products. Okay, so my products, I have CO2 and I have H2O. Okay, I'm going to put 2 brackets because I have 2 things here. How many CO2s do I have here? It's not 0, because if there was 0, then there wouldn't be a CO2. So there's 1 CO2 times. Now I have to look for the heat of formation for carbon dioxide. Okay, so this is where I go to this table. Carbon dioxide is right here. Sorry, that's too high. Right here. Negative 393.5. Okay, so negative 393.5. I'm not going to put my units in so I can save space. Now, since it meant the sum, I have to add my other product. And I have 2 of those guys. So it's 2 H2Os times. Now, for H2O, you have to pay attention. Is it a gas or is it a liquid? So we know it's a gas because combustion gives off heat, and heat changes water to a gaseous form. So that's why I said be careful, because you have a liquid and you have a gas. So the gas heat of formation is different than the liquid, and a lot of students will mess up on this, so be very, very careful. So I'm using the negative 241.8. Okay, now do I have any more products? No, I only have those 2. So I'm just going to put this up here. Reactants are this side. Products are this side. Okay, so since I have no more products, I'm going to close my other bracket because I had 2, remember? So this one here. So I'm just going to change the color of this one so that it's the same. I'm going to make this one bigger because of my OCD. Okay, so let's go back to the formula here. So the sum of the moles times the heat of formation of the products minus. Okay, so I know that between these 2, I have to minus. And I'm making this big so that you can see it and not forget about it. Okay, now I'm going to go to the reactant side. Okay, so I have CH4. How many of them do I have? 1. Okay, so I'm going to put 1 CH4 times. Now we got to look for the heat of formation of CH4. Ooh, right there, so negative 74.6. So I'm going to put in negative 74.6, close my bracket, plus. Okay, now I have to do my next one, which is this guy right here. So I have 2 O2s. So I'm just going to put it down here. I have 2 O2s, and I separate these so I don't put in 20 by accident, times. Okay, O2 is oxygen. Do you see it? Because I don't. Okay, so one of two things could happen at this point. 1, you forgot that one rule, or 2, they didn't give you enough information. Okay, sometimes they'll give you a heat of formation in a question if it's not found in this table. But in this case, down here, elements are given a value of 0. Is oxygen an element? Yes, it is. It's found on the periodic table by itself. So what that means is anything times oxygen is 0. Okay, so you close your bracket, and then you close that big bracket again. Okay. So now to punch this puppy in your calculator. Okay, and you have to be very cognizant, there we go, of your brackets. Okay, so, sorry, get my calculator up. If I can find it, there we go. Okay, so let's start over here. Bracket, 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 bracket. So 2 brackets. Now you can't put CO2 into your calculator, so you're going to just drop the compounds and you just put the numbers. So 1 times. Now again, to get the negative, you put in the number for here, this calculator. In your calculator, more than likely you have to hit negative 393.5. But this online calculator that I have to put in the number first and then hit my negative. It's weird. Okay, so now I have to close that second bracket. Okay, see how there's a gray bracket that's popping up? That's telling you that you have one unclosed bracket. Okay, so don't forget to deal with that after. Okay, now we have a plus sign. So plus, we have another bracket and a 2 times, now I'm just going to move this over, negative 241.8. So 241.8. Going to put my negative in. Okay, and I have to close that second bracket, so the green one here. And see how I have a gray? It's telling me I have to close that blue one. And now it's lit up. Okay, now I minus. Okay, bracket, bracket. 1 times 74.6 negative, and again you might be putting negative 74.6 in the correct order, bracket, plus bracket 2 times 0, close your bracket, and then you hit enter. So you get negative 802.5. Okay, so what are your units? So this is what your handy dandy calculator is good for. Delta RH, find it on here. Delta RH, it's measured in kilojoules. Okay, so you put kilojoules. Now the reasoning behind that is this one is a mole. Okay, so you'd have moles, and then this is in kilojoules, so you're multiplying. So you get kilojoules per mole. And then moles cancel and you're left with kilojoules. Okay, but I just dropped it because you can see how long it gets. Now, when you're doing your calculation, I recognize that not all of you are going to put the 1 times negative 393.5 because you know that 1 times this is just this, and that's fine. Okay? You might also know that 2 times 0 is a 0, so you might not even put it in, and that's fine. Okay. I'm going to do one more with you, and then I want you to try 3 on your own. Okay? So it says calculate the energy change for the combustion of ethanol. Okay? So first we have to balance. So if you struggle with balancing, pause the video and see if you can balance it on your own, and then you can press play. Okay, so we have 2 C's on this side, but only 1 here. So we're going to put a 2 in front to balance out my C's. I have 5, 6 H's. I only have 2 here. So I need to put a 3 because 3 times 2 is 6. Okay, now my oxygens. This is the challenging one. I have 1 here, 2, 3. So I have 3 on this side. And I have 2 times 2 is 4 plus 3. So 4 plus 3 is 7. So I have 7 on this side. And I have 3 on this side. Well, how the heck am I going to do that? That doesn't work. Okay? Because as soon as I change this number out here, it changes out my C's and my H's. So I don't ever want to have to touch this O if I don't have to, which technically means I have only 2 that I can balance with because there's already 1 there. Now, can I multiply 2 by anything to get it close to a 7? So if I go 2 times 3, what do I get? You get 6. Okay? So 2 times 3 is 6, but if I add this one, what do I get? 7. Okay, so let's just do this for a second. So say I put a 3 here. 3 times 2 is 6, plus 1 is 7. 2 times 2 is 4, and then 3 times 1 is 3. 4 plus 3 is 7. So I have 7 and 7. So that's balanced. Okay, so this one's more challenging to balance than anything. So my heat of reaction, or my heat of combustion, bracket, always start with your reactants. So I have 2 CO2s, so 2 CO2s times negative 393.5. How do I know that? Because you work with these puppies so much. Okay, so I know it from up here, or you can use your data booklet. Okay, and it'll tell you right here, negative 393.5. Okay, now plus bracket, I have 3 H2O's on this side times negative 241.8. That's all I have for products, so close my bracket, minus bracket, I have 1 C2H5OH, so that one I don't know my heat of formation for. So C2H5OH. I know that that's ethanol just because I've taught this so many times. But if you don't know, look for the formula here. C2H5OH, ethanol. Okay, you might know this from chemistry. So this is negative 277.6. So I'm not going to fit that there, so I'm going to put it down here. Negative 277.6. Then I'm going to close my bracket, I'm going to close my bracket. Now, why did I do that? Because look here, oxygen. Anything times an oxygen is a 0 anyways. So 3 times 0 is 0, so I'm just going to leave it out. I don't have to worry about it. If you want to put it in, you are more than welcome. So I'm just going to put it in for those of you who are not listening to my video and you just print off the notes. Okay, 302 times 0. There we go. So delta HR equals handy dandy calculator. So here we go again. Bracket. 2 times 393.5 negative, close my bracket, plus bracket, 3 times 241.8. I need to make it negative. Okay, gonna move over. Minus bracket. Now you can go bracket bracket if you want, but I know that this last part is 0, so I'm only going to do the front part. 1 times 277.6 negative, close my bracket. So I get negative 1234. That would be so cool if that was 0.5, but it's not. Okay, so you get negative 1234.8 kilojoules. Okay, laws of thermodynamics, which you should already know. First law is talking about energy cannot be created or destroyed, simply converted from one type to another. Second law says as that conversion is happening, you're going to have waste energy, and that waste energy is usually thermal energy, which is created mainly by friction. Okay, so if you rub your hands together, okay, that is thermal energy, okay, and that gives you the heat. Efficiency we've already done, so I'm not going to worry about it. And then the last one talks about coal-fired generation, power generation stations. So I wrote out the conversions here for you, so I'll explain it in terms of this picture. So we have coal that is pulverized and it goes into the boiler, which will eventually heat, okay, and burn. Okay, so coal is potential energy. Okay, when you burn it, it releases kinetic energy to turn that water in this pipe to steam. Kinetic energy is energy of motion. So steam is going to move at a high speed. Okay, it is then, so water's coming into the boiler, it heats up. That high pressure steam then follows these pipes. At a high pressure, it's going to cause that turbine to turn, which then is kinetic energy of the turbine. Turbine is connected to the generator. So once the turbine is turning, the generator will turn. So that's another kinetic energy. And then that creates electricity, which is moving electrons, if you remember from the last unit. Okay, so those are all of your energy conversions. So each time you have an energy conversion, so in this one you have 4. So each time you had an energy conversion, you would lose some energy. So what that means is the more energy conversions you have in any sort of device, the less efficient that device is. So if I had a different power plant that only had 2 energy conversions, that would be more efficient than 4 energy conversions. Okay, so that is the end of this lesson. You need to complete the Hess's calculation question, Hess's law calculation questions. There's only a couple. I suggest that you get that done today so that it's over and done with. And then you need to watch the nuclear energy videos. Have a great day. Message me if you have questions.